Hello, my name is JMeyers and I am in Electrical Engineering 332 and 342 this semester, and today I'm going to be discussing KI number 4, which is the radio system block diagram. To start off, we have our common source amplifier, which is the start of the block diagram. Now, this initial amplifier is a small signal amplifier, which is referred to as a voltage amplifier, and it's used to convert a small input voltage into a much larger output voltage. And these devices have the advantage over bipolar transistors of having an extremely high input impedance along with a low noise output, making them ideal for use in amplifier circuits that have really small input signals. And following that, we have a characteristic curve equation or graph that details how the incoming and outgoing voltage responds, as well as the signal between your drain and source, and going on from there. We can see our quiescent point here, and it details biasing for the amplifier. Now, moving on, we have our mixer, and the mixer and local oscillator work in tandem, and the mixer purpose is to change the frequency of an electromagnetic signal while preserving every other characteristic, like the phase and amplitude of the initial signal. A reason for frequency conversion is to allow amplification of the received signal at a frequency other than that of the radio frequency. And following from this, we can see how the local oscillator helps. And so the local oscillator acts as a gate of the mixer, in which the mixer is considered on when the local oscillator is a large voltage and off when it is a small voltage. And what we can see of the oscillator that assists the mixer is a tank circuit, which you can see here, which holds charge and current, and we can see that the capacitor and inductor actually work in tandem, switching between our A and B here once our capacitor discharges, and once that happens, the inductor resupplies current into the tank circuit, and it continues from there. And the local oscillator assists in taking that DC voltage and translating it into that AC voltage. Now, we have our power amplifier, and the difference between this and our regular amplifier is that power amplifier converts the DC power drawn from the power supply into an AC voltage signal delivered to the load. It's a high amplification and is high efficiency, but the AC voltage signal output is particularly poor, and that's why we end up needing a bandpass filter, which we can see has a high pass filter and a low pass filter. So we are going to be attenuating the signals so that we only have a particular bandwidth of frequencies going into our next stage, which is the diplexer. Now, the diplexer is a unit that enables more than one transmitter to operate on a single RF antenna. Typically, an antenna diplexer would enable transmitters operating of different frequencies to use the antenna. Similar properties to the bandpass filter. Now, going into our final slide here, as the antenna is concerned, we see that electromagnetic waves have both an electric and magnetic component that are inseparable. The planes are right angles to one another. The electric field results from the voltage changes occurring in the radio frequency antenna, which is radiating the signal, and the magnetic changes result from the current flow. It is also found that the lines of force in the electric field run along the same axis as the antenna, per Faraday's laws. And this electric field is measured in terms of the change of potential over a great distance. And then over here on our left, we can see the radiation pattern that comes from a dipole antenna. Radiation is the term used to represent the emission or reception of wavefronts at the antenna, and it specifies its strength, essentially. The energy radiated by the antenna is what we see as this radiation pattern. So thank you very much.